beginning of our lecture about e to the z. Certainly, because z is x plus iy, e to the z will be e to the x plus iy. Because of the properties that the exponential will have, and by the way, all of these exponential properties can be proven from the power series. You see, we don't need the real interpretation. The power series will give us all of these results, but again, we'll drill on those in the exercises. I just want to get the highlights here. This is e to the x times e to the iy. But notice here, you see, that y is real. And or even if it wasn't real, it doesn't make any difference. E to the iy is cosine y plus I sine y. Multiplying this out, e to the z is e to the x cosine y plus I e to the x sine y. The important thing being that because y is real, e to the x cosine y and e to the x sine y are both real. And consequently, if I let u denote the real part and v denote the imaginary part as usual, what I have is that u equals e to the x cosine y, v equals e to the x sine y, must be a real conformal mapping. Why? Because the real and the imaginary parts, make up an analytic function. How do I know this function is analytic? Because its power series exists. And the fact that its power series exists means that all of the derivatives must exist. Now, again, I didn't write this in here, but maybe it's a worthwhile aside to show you what this conformal mapping looks like. For example, notice that if I square both sides of each equation here and add, if I square and add, what do I get? On one side, I get u squared plus v squared. On the other side, I get e to the 2x cosine squared y plus e to the 2x sine squared y. I factor out e to the 2x, and that gives me e to the 2x sine squared y plus cosine squared y, which is 1. So this is just u squared plus v squared is e to the 2x. To eliminate x from the equations, I can divide the bottom by the top, and I get that v over u is equal to tangent y. And by the way, notice what this thing tells me. This tells me, see, what are the basic lines in the xy plane? They're the lines x equal a constant, y equals a constant. Notice that if x is a constant, this says that u squared plus v squared equals e to a constant power. That's u squared plus v squared is a constant. That's a circle centered at the origin. In other words, the lines x equal a constant map into concentric circles. On the other hand, if y is a constant, this says that v over u is a constant. In the uv plane, v over u is a constant is a straight line that goes through the origin. See, v is a constant times u. Now, what that means pictorially, let's see if I have some room to squeeze this in here. What this means pictorially is that this kind of a network, see, in the xy plane, this kind of a network in the xy plane is mapped into what? This network is mapped into a, what? The vertical lines go into concentric circles, and the horizontal lines go into lines through the origin here. And not, okay? Notice, by the way, that every line through the origin meets the circle at right angles. Notice that these lines were at right angles here. Notice the conformal property here. In other words, lines that meet at right angle in the xy plane must meet at right angles in the uv plane. And let me separate this out from anything else that I've done so that we don't get too mixed up with this. By the way, one of the ways that this is used in application is with the inverse mapping. That in certain cases where we have to deal with regions that have this kind of a shape, we back map this region, and what will it go into? It'll go into a rectangle here. And for example, in solving Laplace's equation, it might be a lot easier to solve Laplace's equation on the boundary of a rectangle than on the boundary of a region of this particular type. Again, I don't want to go into too much detail here because it obscures what the main overview is. Namely, every time we invent an analytic function like e to the z, sine z, cos z, etc., we have invented a new conformal mapping. Whether that conformal mapping will help us in a particular application or not depends on the application, but what the meaning of it is independent of any application.